Well, dear students, now something left while teaching. Types of diffraction. Two types of diffraction are there: Fresnel diffraction and Fraunhofer diffraction. Diffraction of light, take place when any wave passes across any obstacle or passes through any opening hole, then wave bend around the corners. I told you in sound it is easy to observe because size of wavelength of sound is very large in comparison to light. Anyway, so what is Fresnel diffraction? In this diffraction, source of light and screen on which diffraction is to be observed are placed at finite distance from the diffracting obstacle or aperture. As on the figure, here is the source of light, this is the hole, this is the screen. So this is definite distance, this is also definite distance. So this type of diffraction observed by us is called actually Fresnel diffraction. I told you, I am telling you, because sometime in exam they ask by question is asked by name of diffraction, Fresnel or Fraunhofer. So student may get little puzzled, and in complete exam this is not desirable to get puzzled. You have to be there with full confidence. Now Fraunhofer diffraction. It is the diffraction. In this diffraction, source of light and screen are placed at infinite distance from diffracting obstacle or aperture. How? Actually, जब infinite away है तो how it is there? Parallel lines or parallel rays meet at infinity. So what they do actually in this diffraction figure is like this. We put here a lens and the source is placed in focal plane of this lens. So from this, if this point lies in the focus of convex lens, there is a focus that there is a point from which the diagonal will become parallel. So if they are parallel, they are supposed, then the source supposed to be at infinity. The source here, but we make it at infinite distance by putting source at focus of this lens L1. Now, from here, we get again parallel type of beam. We use L2, and that light falling on this from here like this, so they appear to focus at this point here or here. So screen and that is supposed to be at infinite distance. It is in focal plane. So they appear to fall on this lens L2 parallel. So this is called Fraunhofer's diffraction. So you may be asked by this. Actually, I have explained using the diagram there. A plane wave front is incident on this. हमने diagram बनाया था कि this was a large view of the slit, plane wave front, and plane wave front there it means rays normal to the wave front are called rays. So they are supposed to be coming from infinity here, and then I told you 2.0 will be at large distance and wavelet from here will be going like this. So if we use here a convex lens, that will converge then in focal plane. I have told you while teaching lens, if rays parallel to principal axis are zero, they get focused or they converge at a point on principal axis which is focus. And if they are not parallel to each other, they are parallel to but not parallel to principal axis. They are parallel to each other but not parallel to principal axis. Then they will get focused at a point lying in focal plane. This will be focal plane. So that fact is used here. This is focal plane. So I have the intention to tell you about this name only, Fresnel and Fraunhofer. In numerical, the names are given. Now I want to discuss here a question with you from NCERT book. That is 10.9 question. 10.9 question, so unsolved examples of NCERT. Just for practice, simple question है, not so difficult. But if you don't solve first before exam, then we are unable to solve it there. A parallel beam of light of wavelength lambda 500 nanometer. I used to tell in kilometer. Fall on narrow slit and resulting diffraction pattern observed at 1 meter away. A narrow slit. Here is 1 meter distance of the screen. It is observed that the first minimum is a distance of 2.5 millimeter. Actually, this distance here is given 2.5 millimeter. By here, first central maximum means bright intensity, and finally we get 0 here. So what is the width of the slit? What is A? ये जो slit width है ये क्या होगी? This angle theta will be the angle subtended by this 2.5 millimeter on the slit, or this is also called angle spread. We know that angular spread by angular spread of light from a narrow slit theta equal to lambda by A. Theta. Here theta, so I told you it should be like this. A sin theta is equal to lambda by A, or sin theta lambda by A. But I told you many times, when theta is very small, then sin theta is equal to theta. If you have any trouble with this, when theta tends to 0, though I have explained in one of my video, general mathematics used in physics. So theta tends to 0. Tends to 0 means theta is small angle, not 0. And this approximation is true up to 15 degrees, 0 to 15. So theta times sin theta. I have told you here, when we use this, or this theta, both should be put in radian, not degrees. But when theta is very small, and when theta again tan 0, theta equal to tan theta equal to here this non suppose it is y and this is d, y upon d. So comparing the two we get क्या मिलेगा भाई? lambda upon A is equal to Y upon D. We need A, lambda D upon Y. Lambda 500 nanometer, put this into meter. D 1 meter, Y 2.5 millimeter, 10 to power minus 3 meter, millimeter. Actually milli means 10 to power minus 3. So millisecond, millimeter, milligram, all this milli 10 to power minus 3. So now you can solve it easily. That A will be how much? 10 to power 5. So 5 into 10 to power minus 4 upon 25 decimal here. So it is 2 into 10 to power minus 4 meter. But converts into millimeter, it will be 0.2 millimeter. So this question actually explain you a little fact. Simply, please, and I will explain while teaching diffraction due to single slit. So this was one question here. Now, before I go to the question, there is an objective type question here. That is 10.17. 10.17. Answer the following questions. You can see the book. This question is very important for 12th class exam. CBSE asks such type question very frequently. In single slit diffraction experiment, width of the slit is doubled. Width of slit is doubled the original width. How does it affect the size and intensity of central maximum? भाई ये diffraction pattern is observed from the slit here, so we get this, suppose this width. Now he says if we increase this width, how will the width of the central maximum be affected and intensity? As we know, theta equal to lambda by A. If we make A dash equal to 2A, then theta dash will be lambda by 2A. यानी कि theta by 2. यानी कि width will reduce to half. The width of central maximum will reduce to half. Then intensity, if we increase double radius करते हैं, तो area will become 4 times. So intensity of light falling here will increase 4 times. तो क्या कहेंगे यहाँ? Width of central maximum reduced to half. While intensity of central maximum will be 4 times, because pi r square, r 2r whole square 4. So more light will come. So this is a part of this question has been asked in board exam. Second question is there. In what way is diffraction from each slit? In what way is diffraction from each slit related to the interference pattern of double slit experiment? Young experiment, we use 2 slit in young experiment. तो जो यहाँ इंटरफेरेंस पैटर्न seen, तो that interference pattern will be observed, will be the result of interference to slit and diffraction pattern from each slit. The pattern, the interference pattern will be superimposed by diffraction pattern of each slit. This is the answer. You can read in the book. When a tiny obstacle is placed in the path of light from the distant source, bright spot is seen on the center of the shadow of the obstacle. Explain why. They say here, when tiny circular obstacle is placed in the path of light from distant source. Distant source means parallel beam light is coming. Here is the parallel beam and we place circular obstacle, small obstacle. So here you are supposed to get shadow, but we get a bright spot. Why? Because the light get diffracted, get bent around the corner and produce from every edge, all around the edge, circumference is there. So from every point of the edge, light bend towards the shadow and produce bright light. It is because of diffraction, you can say. Two students are separated by 7-meter partition wall. Partition wall is there. One is both this side and this side. 7-meter partition wall, 7-meter partition wall is room 10-meter high. Wall is 10-meter, distance between them 7-meter. If both light and sound waves can bend around obstacle, how is that? Is it that students are unable to see each other even though they can converse easily? दोनों आपस में they can talk each other but can't see. While light is also wave phenomena, sound is also wave phenomena, and wave get bent. So it is. I told you that for diffraction to occur, the size of obstacle should be of size of wavelength. Wavelength of sound is of meter order, and hence sound wave can get bent easily, while the wavelength of light is of angstrom, so that cannot bend too much. So they cannot see because wavelength of light is very small. This question has also been asked in board exam. Okay, now actually video has become 18 minutes. I will take more question in other video, numerical problem which make you clear about the facts which we use.